This is Mr. Martin. These are video notes for Pre-Calculus Advanced. We're in Unit 9. This is Section 9.4, and we're going to continue with vector operations. So with vectors we have two basic operations. We have scalar multiplication and we have vector addition, which also would include subtraction. Remember from algebra, subtraction is just addition of the opposite. So when we talk about vector subtraction, really we'll just convert it to addition of the opposite, but we'll get to that in a minute. So for scalar multiplication, a scalar multiple of vector v is given by some value c times the vector v, where c is some real scalar, so it's some real number. Alright, this new vector cv is c times as long as v. So if c is less than 0, then the new vector cv would point in the opposite direction of v. So let's take a look at this picture over here. Here's my original vector v, and then here are several scalar multiples of that. So this first one is half v, so our value of c is a half, so we can see that it's half as long, but it goes in the same direction. The next one is 2v, so again it goes in the same direction, but now it's going to be twice as long. Its magnitude is going to be twice as large. Here our value of c is -1, so you can see it has the same length, it has the same magnitude, but now it's going in the opposite direction. And then here, the last one, our value of c is -3/2, so again that negative is going to put it in the opposite direction, and it's going to be 3/2 as long as the original. Alright, so when we're multiplying by a scalar, remember this vector v has an x component and a y component, so you're going to want to multiply each component by whatever that scalar value is. Alright, and then for vector addition can correspond to a combined or net effect. So if v and w are force vectors, the resultant, so this is an important vocabulary word for you, because if the problem asks you to find the resultant, you know you want to add the two vectors. So the resultant vector v plus w represents the net force. Alright, and then again vector subtraction is defined by addition of the opposite. So whenever we have those, I'll change it to addition of the opposite. And when we're doing this, we're going to do it algebraically and we're going to do it graphically. So there's a couple different ways to do it graphically. The one I'm going to talk about in the video is called the parallelogram law. So basically we're going to take the two vectors that we have. In this case I've got vector A, and I've got vector B, and we're going to add these. So what we're going to do is we're going to use these two given vectors as two adjacent sides of a parallelogram, and we're going to complete the parallelogram using equivalent vectors. So if I have vector B over here, I'm going to come over here and I'm going to dot in another vector that's equivalent to B but starts at the end of vector A, and then I'm going to come over here and draw an equivalent vector to A. So now I have this parallelogram, and basically the resultant is going to be starting from where the two vectors began. So to draw A plus B, we draw A and B so they have the same initial point. So here's my initial point. Initial point. Okay, then construct the parallelogram, if any, that they determine. So here's my dotted blue and dotted red vectors to complete the parallelogram. And then we're going to draw an arrow from the common initial point to the opposite corner of the parallelogram. So this is the diagonal of the parallelogram, which becomes the sum of the vectors. So here's the diagonal, and this becomes the resultant A plus B. Alright, so this works really well if we just have two vectors that we're adding or subtracting. If you know another method from physics, it's perfectly fine to do it that way as well. Alright, so moving on, some more vector properties. We've got u, v, and w are vectors, and c and d are scalars, and these properties are true. So if you want to pause the video and kind of look over these properties, really many of them work the same way that things work in algebra. Okay, just similar properties, you know, distributive, associative. They work with vectors as well. You just have to be careful because now we're working with x components and y components. So let's practice with these properties. Let's work on these examples. If at any time you want to pause the video and work through these and see how you do, I encourage you to do that. So this would be a good time to pause if you want to try and do these. So we want to find each of the following, and then we're going to sketch a geometric interpretation. So for u plus v, since I have u is 1, 2, and v is 3, 4, u plus v, so what I want to do is I want to add the x component of u to the x component of v, so it's 1 plus 3, and then the y component of u to the y component of v, that's 2 plus 4, and this would give me 4, 6. Alright, so this is the algebraic method. Now if we want to do a geometric, let's go ahead and graph each of my vectors. So I've got 1, 2, 3, 4. Let's just go out to 6. Let's go up to 6, 4, 5, 6. And then I've got u is 1, 2. So here's u. And v is 3, 4. So 3, up 4. And if I want to add these, I'm going to use my parallelogram method. So it's a little bit squashed here. So what I'm going to do is I'm going to make a dotted vector that's the same length and direction as u. So I'm going to do this over here. And then I'm going to do this over here to make my parallelogram. Again, it's kind of squished there, so it's hard to tell. And then my net force, or my resultant, is going to go from the initial point here through the diagonal to the other side of the parallelogram. Alright, so this red vector, hopefully if I did that right, that's about 4 and 6. 4, 6. So your result should match your algebraic result as well. Alright, so now let's do u minus v. So I'm going to change this to u plus the opposite of v. So now I'm going to find the opposite of v over here to use for my calculation. I'm just going to take the opposite of my x and y components. That would be -3, -4. So now u plus the opposite of v would be 1 plus -3, and then 2 plus -4. And that would give me -2, -2. Alright, so again, there's the algebraic method. If we want to do the geometric, let's go ahead and graph these out. So I've got u as 1, 2. So there's u, and then the opposite of v is -3, -4. So somewhere over here, and then again, it's a little bit squished there because these are pretty close to being collinear, but we'll we'll work it out. So I'm going to draw in my parallelogram, and then I'm going to go from my initial point where the two vectors started and go along the diagonal. And I'm a little bit off on this one, but you should get the idea there. And then that point there should be -2, -2. When I give you these on a quiz or a test, keep in mind that I'll give you a coordinate grid to graph these on, so it'll be a little bit more accurate. Alright, so if you've been working these out on your own, hopefully you've been doing okay. If you do have questions, again, make sure that you ask. For part C, we've got 2u minus 3v. So the first thing that I'm going to do is I'm going to find 2u. So that's just going to be 2 times 1, 2. So that's going to be 2, 4. And then I'm going to find 3v. So that's going to be 3 times 3, 4. So that's going to give me 9, 12. Now, when we're doing these algebraically, it's pretty straightforward just to subtract these. So then I would have 2u minus 3v, and that's going to give me, so I've got 2 minus 9, so that's -7, and 4 minus 12, which is -8. Alright, so feel free to go ahead and try and do this one graphically as well. And again, if you have any questions, make sure you ask. And you should have gotten a practice packet in class as well. And we've got one more problem at the end here. A couple more problems. So I'm going to put solutions to these problems in another video, and we'll see you next time.